back in like 30 weeks ago.
Okay. So here is what a sampling distribution might look like. All right. So now the top curve here you see is the population. So this is not samples. This is all the individuals in the population. All right. And we obviously can see it's in normal in shape, right? So if I take a sample of 5, there's my sample of 5 right here. Distribution of means for 5. So I took 5 samples of 5. And you can see, okay, so the population mean at the very top in the blue. So the true population is 16. Do you see that? And the mean of the true population is 16. The mean of my distribution down here with just 5 little samples is 15.74. Pretty close, right? If I keep taking samples, 1, 2, 3, 4, 5, and drop that mean on there, let's say if I do it 10,000 times. So look, it's normal in shape. The sampling distribution, the blue thing, is normal in shape, right? No surprise there. That's what we did. That's what we experienced in the past few days. Even with samples this small, of size 5, it's still normal in shape. So then the question becomes, well, what happens if it's not normal in shape? So we're going to change this up. I'm going to change this one to a skewed distribution. This is right skewed, all right? What happens if I take samples of 5 and do a bunch of them? Okay, we can't see enough yet, but let's say if I do 10,000 of them, it's kind of normal, but it's still kind of skewed too, right? You see it? So it kind of looks like the original population. So this is too skewed for us to use norm CDF, so it's still an issue. And notice that the means are still pretty close. The medians were fairly close. But that's if I took 10,000 samples. So what if I did only 5 samples? Or 5 more? 5 more, 5 more. Begins to get there. But here's what I want you to see. If I change my sample size from just 5 in all my samples, let's go up to the highest this will allow me to go to 25, all right? If I take a whole bunch of samples of size 25 from this population that is skewed, look what happened. It's very normal now. Do you see it? It's very normal, and the only thing that changed here was the size of the samples that I took. All right? So this is what we call the central limit theorem in statistics. It's really important. It's really handy. You will love it before this year is over. Because it saves us a lot of time. So when it comes to finding out if our sampling distribution will be normal and we're dealing with means, all you have to do is look at the sample size. If it's large enough, we know the sampling distribution would be normal without doing all the work. Isn't that nice? So then you might be like, well, what if it's really messed up? Like, I'm going to custom make a distribution here, okay? Like, do something weird. Something like that, right? Multimodal, all the things. What the heck is a sampling distribution going to look like with that? Well, if it is samples of size 2, let's make it really, really small. It's sort of normal, right? Yeah. What if I make it samples of size 25? It gets really normal. You see what I'm saying? Much less variability. Remember, we want lower variability? Much less variability here, which is the ideal. So it doesn't matter what shape it is. Let's do another custom that's really weird. You want to do a uniform? You want to see a uniform? What happens if it's uniform? Samples of size 25? Boom. Becomes normal. Crazy, eh?
Nice.
What's that? What? So what if it's skewed like that? Like really, really, really skewed? Normal. Isn't this handy? Somebody figured this out. Somebody did thousands of samples and discovered it was going to happen every time if your sample is large enough. All right? Now, it's when
SE is supposed to be
what is this? When n is greater than or equal to 30, that's the magic number here. I know the applet did 25, but the agreed upon number in the stats community is 30. When the sample is greater than or equal to 30, then the sampling distribution of X bar is approximately normal regardless of the population shape. All right? If it was less than 30, then it's going to be whatever shape the population was. It's like if it was right skewed and your sample was 10, then the sampling distribution would be right skewed as well. Make sense? So that 30 is the magic number. Keep in mind, this only applies to means. It does not apply to proportions. It only applies to means problem. Now, normal problems. When we find area under the curve, sampling distribution of X bar, it's the same thing we were doing before. So we would do the X bar minus the mean over sigma divided by the square root of n. This is exactly what we did yesterday. So the only thing we're adding to it today is, how do you know if it's normal? We have a new tool, the central limit theorem. All right? So here's a little memory thing. We sometimes abbreviate the CLT, not to be confused with the BLT. But the CLT, you can only get it at the X bar. You, no. Nobody got that joke. Okay. You got it? CLTs, you can order a CLT at the X bar?
Yeah.
Yeah, thank you. But you can't get it at the P hat.
What's a CLT?
Central limit theorem. X bar is the mean of a sample.
You can get a CLT at the X
Shut up, you're confusing me.
I was trying to be helpful, but whatever. Okay. Among iPhone users who share data with Apple, the weekly screen time is skewed to the right. Skewed to the right, all right. With a mean of 13.5 hours and a standard deviation of 3.75 hours. Random sample of 100 users are selected, and the mean likely screen time of X bar is calculated. Describe the shape of the sampling distribution for X bar with samples of 100 randomly selected users. Justify your answer. What would this shape be? Why?
Because it's greater than 30.
Because it's greater than 30. Boom, that's it. So it's going to be approximately normal. And here's your justification. You would say n is equal to 100, which is greater than or equal to 30. But you can't stop there. 30 needs a connection. Otherwise, it's some arbitrary number you pull out of air. 30 by CLT, central limit theorem. CLT. So you will lose points if you just say greater than 30. Check. That won't work. It has to be by the CLT. CLT has to be connected to that 30. All right. Now, find the mean and the standard deviation of the sampling distribution. This is just review from what we've done. It does say check that 10% condition. Why do we need to check that? Do you remember? That's to check for independence, which allows us to do the standard deviation calculation. Yes. So let's check that 10% condition. All right. Is 100, it's 100 teenagers, right? 100 users, not teenagers. Is 100 less than 10% of all iPhone users? Is that a reasonable estimate?
Yeah.
Yes. So that's the way I show my work. I have thought through it. 100 is less than 10% of all iPhone users. I put it in context. Yes, we can proceed as if this is independent. Okay? So then it says, what is the mean of all the samples going to be? Yeah, just whatever the true mean is, which they told us was 13.5. The standard deviation of all my samples, according to your formula, it's just the standard deviation divided by the square root of my sample size, which was 3.75. What's the square root of 100? 10, which means I move my decimal one place to the left. You have a calculator if you don't. It's less than or equal to. Yeah. All right, so I have my new standard deviation. It went down quite a bit, didn't it? All right. Calculate the probability that the weekly screen time for the sample is between, so this is for the sample, that means I use my new standard deviation, between 12 and 13 hours. So I draw myself a little picture, put the mean on there, which was 13.5. What's the probability? The sample mean is between 12 and 13. So it's this little piece right there. So where do I go now? Norm, CDF, lower boundary of 12, upper boundary of, good. The mean is 13.5, and sigma is 0.375. And let's see what we get. Point 0.0912. So a 9.12% chance that the average screen time for a sample of 100 users is between 12 and 13 hours. Yeah? Not so bad, eh? That's it.
That's pretty easy.
That's it.
I might pass this test.
You will get this too. 7.2. All right. 7.3 has to do with means, and we'll come back and do this just as way of review in a minute. All right. Now, when we did the means, we said the average when it comes to sampling distributions, right? We need to know for both of these, we're going to need to know the mean, the standard deviation, and is it normal? What's the mean? What's the standard deviation going to be? And then is it normal? So, with means, we said the mean of all the x bars is equal to the true population mean, right? Nothing new there. Standard deviation would be the population standard deviation. And then what do we do to that? Over the square root of n, right? And then, of course, you have to check that 10% rule, right? That's in there. You got to check that condition. The normal condition is when we have to check. Now, with means, we have two ways to do that. Okay? One option is that it's given the population is normal. That's what we looked at yesterday. If the population is normal, we know the sampling distribution is normal. We're safe to proceed with norm CDF stuff. We have to check this to prove that we can use norm CDF. And then today, we learned our second option. If n is greater than or equal to 30, we know it's normal by the CLT, the central limit theorem. All right. There is a third option. We're not going to deal with it right now. We will in chapter 8. What if they don't tell you it's normal? What if the sample's less than 30? What are you going to do? Something you won't like, but we'll do it. It's not going to kill us. All right. There's a third option. We'll just put in here chapter 8. We'll talk about it. Come back for more next year. All right. Now, that's all section 7.3. Can we live with that? Yeah, not so bad. 7.2, well, 7.1, I just explained to you what sampling distributions were. All right, a bunch of samples, right? With the mean with the proportions, we said the mean of all the p-hats is equal to the true proportion that was given, right? The claimed proportion in the question. Remember, proportions are percentages, right? Yeah? Means are averages, right? So half of this is reading the question, deciding which lane you're in. All right, standard deviation. This is on your chart. You have to do that big square root thing. Remember this? have to calculate it. Yeah? Sample size will make it smaller, right? Bigger sample. We still have to check that 10% condition. Still an issue. All right. And then how do we know if it's normal in its percentages? What was that test? Good. Large counts test. You can only use this with a percentage question. And if you remember, this was n times p is greater than or equal to 10, and n times 1 minus p greater than or equal to 10. If it passes, then it's approximately normal. Both of them pass.
Do we get in the picture?
No, I don't. But
You're in the picture.
that's it. That's the entire chapter in a nutshell, right there. Can we do this? You can.
Confused for a little bit.
Sometimes the hardest part is keeping track of your symbols, right? P hat, X bar, mu, P, knowing what they mean, figuring out what's going on. You can absolutely do this, and you can absolutely do amazing on the test sat